In this video, we're going to talk about this dude, Cramer. No idea who he is. For all we know, could have been the guy on Jerry Seinfeld's couch. Probably not. Hopefully. Oh, man. Am I dating myself with that? I don't even watch that show, but here we go. Okay. As we descend into madness. Couple more types of matrices we got to talk about. The AIB matrix. And just for fun, I threw our other notation for B in there by typing it. Why not, you know? And again, so this is a vector versus a matrix. So if I have the matrix equation AX equals B, the AIB matrix is the matrix with the ith column. So notice, generally we think of J on the column. The I is there on purpose. Trust me on this one. I had a moment with it myself. But the ith column of A, so just whatever number column of A, replaced by whatever our vector B is. So here's an example. I don't know. Let's let A be 1, 2, 3, 4. And I don't know what X is. And will that B be, I don't know, 7, 8. So the A1 B vector or matrix would be my first column replaced by our B vector is 7, 8, so then the 2, 4 stays. So this guy goes in right there. Same thing, the A2 B vector would be replacing the other side. Would be our 1 and 3 stay, but this time the 2 and the 4 are going to be a 7 and 8. So what we're going to do, Cramer's rule says we're going to use this idea to help us solve or find unique solutions to our AX equals B equation. So far, we have figured out how to solve this by doing row operations. We've figured out how to solve it by finding inverses. And now we're going to figure out how to solve it by using Cramer's rule. Cramer's rule says that each entry is given by the determinant of that AIB matrix. So notice, so whatever position X I want, that's the column that I'm going to replace B with, and then find the determinant of that matrix, divided by what the determinant is of the original A matrix. All right, let's put this into action. Ready? So we're going to use Cramer's rule to solve this system. Again, another way we could solve it, we could find an inverse. It's a 2 by 2 system, which is great because I could do a real quick inverse. And hey, we're going to do that in just a minute. Or we could do row operations to solve this, but we're going to use Cramer's rule, see how this goes. So a couple things we need. Well, first, we need a matrix equation. Right now we have a system. We need a matrix equation. So we need our coefficient matrix is 3, -2, -5, 4. We have some x1, x2, doesn't even really matter. And our B vector is 6, 8. So there's B, there's A. That's helpful. Now we need a couple of things. So I'm going to need to find an x1 and an x2. So if we use this definition up here, x1 is defined by the determinant of the A1 B vector divided by the determinant of A. x2 is the same thing, except for this time we're going to take the second column replaced by B, find its determinant, and then the determinant of A. So we need a couple things. So we need the A, again, the screen. The A1B vector matrix is equal to, instead of the 3, -5, I'm going to replace it with the 6, 8. So we have 6, 8, and the rest of it stays, -2, 4. We need the A2 with B replaced. So this time we're replacing the second column, so 3, -5, 6, and 8. And we're also going to, and now we need some determinants. So we need the determinant of this guy. That's equal to 6 times 4 minus 8 times -2 is going to give me, if I can do math, which, you know, we've determined most of the time I can't, 40? 40. And this guy, so the determinant of this guy, the A2, with the B vector inside of it, is 3 times 8 minus 6 times negative 5. It's going to give me 54. Why not? And lastly, the determinant of A. So the determinant of A is, we're going back to our original A here. I'd have 3 times 4 minus negative 5 times negative 2. Everything gets all washed out, and I get 2, which is nice. So now we have enough information to figure out what the solution to our system is. So this is 40 divided by 2, which is 20. And that one's 54 divided by 2, which is 27. So our our x vector in this, that's a unique solution to this equation, is equal to 27. There we go. Yay! Party! All right. Let's compare that to finding the inverse. And we're going to compare the solution. So we're going to find the inverse for a reason. And then we're going to find the solution to this system instead. So what I'm going to do is I'm going to take the same coefficient matrix, but I'm going to make it the homogeneous, or not homogeneous, almost homogeneous. And I'm going to solve and see what happens if I do 1, 0 instead. There's a reason for this. It's going to be cool, I promise. So first I need to find the inverse. All right, so we already know the determinant of A, which is great, which means that the inverse of A is equal to 1 over the determinant. So 1 over the determinant, 1 half. I'm going to switch the positions on my diagonal. So the 3 becomes a 4, the 4 becomes a 3. And then on the secondary diagonal, I'm going to change the signs. So the negative 5 becomes a positive 5, and the negative 2 becomes a positive 2. And I'm just going to simplify here, so I get 2, 1, 5 halves, and 3 halves. Keep that in mind. All right. Now we're going to use our Cramer's rule again. So this time our A1B is 1, 0, negative 2, 4, which gives us a determinant of 4. Our A2B is 3, negative 5, 1, 0, which gives us a determinant of 5. Right, because 3 times 0 is 0, minus negative 5 times 1 gives me a positive 5. And that means that my x1 position is 4 divided by 2. My x2 position is 5 divided by 2. That's 2. Oh, what do you notice here? Oh, interesting. Very, very interesting. Hold on to that idea. Okay, well, all of like 2 seconds. This guy right here, that's the first column of the identity of this I2, right? 1, 0, 0, 1. Oh, hey. And it turns out if we'd done the other one, if we did this system, negative 5, 4, x, and we reversed it, did the other column, we'd end up with these guys. Oh, cool. Turns out we can use this idea to get us, so we can use Cramer's rule and replacing different rows or replacing our solution by vectors that are pieces of our identity matrix. Okay. So some more definitions of vectors. The EJ vector is just the jth column of the identity matrix that matches the size of A. That's it. All it is. So we're going to use this to find our inverses. So the downside to this is if I have a lot of entries in my matrix, I have to do a lot of determinants. And the larger my matrix, the more involved those determinants are. Now, it gets a little nicer because we're replacing rows and columns by ones and zeros. And by rows, I mean columns with ones and zeros. So those determinants are a little bit easier to find. But here's how this is going to work. So to find the determinant of our AEJ matrix, we're defining that, and it turns out that it becomes the cofactor of the JI position. Just roll with me on this one. So notice it's flipped. So normally, as we go down the matrix, right, this is the A11, this is the A21, A31, so on, right? This number changes as the rows go down. And when we go this way, it's the column number that changes. Notice for our cofactors here, it's a little bit different. So it turns out this thing here, this is the transpose of a matrix made up of the cofactors of each position. And this has a special name. We call this the adjoint matrix, or we call it the, starts with an ADJ. I don't know. We call it the adjoint matrix, or we call it the adjugate matrix. Adjugate. Now you're more likely to probably to hear the adjugate. The adjoint apparently means something else further into weird linear algebra space, but we don't have to worry about that. So we just we call this the ADJ. So the adjugate of A is a transpose of the matrix of the cofactors of each position. So right, this is the A12 position, but I want the cofactor of the 2,1 position. Hopefully that makes sense. So here's what that looks like, and it boiled down to a really, really small, tiny little formula. So let's try this out. So the first thing I'm going to do is I'm going to actually make a, I'm going to make myself kind of a, I'm going to organize my information here. So the first thing I'm going to do is I know that I need to find the cofactor of the 1,1 position, cofactor of the 1,2 position, the 1,3 position. And I'm organizing this right now, at least to help myself out, in terms of their positions in the matrix as they stand right now. And the reason I'm doing that is just to help myself out. So then I have the cofactor of the 2,2 position, the 2,3, cofactor of the 3,1, 3,2, and 3,3. Now, those are all just a little bit too big, aren't they? Oh, goodness. Okay, so stop it. Oh, okay, we'll move those around. Those guys, because we're going to need some more space, aren't we? Okay, so our cofactors. Again, we're going to need our positive, negative thing. So I'm going to throw that in here. Because that's just going to tell us, and I'm not even going to bother. I'm just going to use that right now. Again, we don't need, so for the cofactors, we don't actually care about the coefficients. That we're not multiplying by the coefficients because we're not finding the determinant right now. We're just finding the cofactors. So my cofactors, I know that this cofactor, because it's positive, I'm going to have a positive, and that's what happened. And this is the cofactor for when I get rid of the first row and the first column. So I'd need to find the determinant of what's left. So the -1, 1, 4, -2. Now, nicely, because this is a 3 by 3 matrix, those cofactors have a matrice that's easy to find the determinant of. So go through, find all your cofactors, pause the video, come back and see how you did. How did you do on your cofactors? Hopefully you did all right. So as a reminder, our formula here, what we're going for is that the inverse, A inverse, is equal to 1 over the determinant of A times the adjoint or the adjective matrix of A. Now, we found all our cofactors, so now we need to find our adjective matrix. So our adjective matrix of A, it would be really tempting just to take each of these numbers in the position they're in, but we're going to take the transpose of the position that they're in. So the adjective matrix, we're going to take the -2, 3, 5 is going to be the first column. 14, -7 is going to be the second column. And 4, 1, -3 is going to be the third column. Now, it may seem like it's going to be hard to find the determinant of A, but we have all of the things. Why did that word just leave my brain? We have all of the things, and so all we need to do is pick one of the rows or one of the columns and take the sum of that row or that column times the positions. So might as well, I don't know, do the first one. So I'm going to take the first position, 2, times the cofactor, which is -2, plus my second position, which is 1, times my second cofactor is 3, plus my third position, which is 3, and again, I'm just going along the top row, times my third cofactor, which is 5, right? And I have already baked into those cofactors the positive negative thing, so I don't have to worry about that anymore. So this is going to give me a beautiful determinant of 14. Yay! Right, so I have 15 plus 3 is 18, minus 4, 14. Yay! So now we can figure out that our A matrix, or our A inverse matrix, all we're going to do is we're going to take this adjoint matrix and we're going to multiply by, so we're going to multiply this by, our A inverse is the adjoint matrix where each term is divided by 14. So I get -1/7, I get 1, I get 2/7, I get 3/14, -1/2, 1/14, 5/14, -1/2, and -3/14. And there we go. There is our lovely, lovely inverse matrix. And surprisingly, a lot less work than if we had tried to find the inverse matrix using our, what we've done before is we took our matrix and the identity matrix, and then we did our row operations to switch the positions to get the identity and then the inverse. This might seem like it takes a little bit longer, but one way or the other, it's, there's positives and negatives to all of the things that we might do to find any of these things. All right, another fun fact. You ready? You ready for this? Now, we didn't actually have to do this process right here. What we could have done, if we take the fact that we've determined that our inverse is equal to 1 over the determinant times our adjective matrix, and we know that A inverse times A is equal to the identity, well, I'm going to do a little bit of fun algebra here. You ready? So I'm going to take and I'm going to multiply both sides by the A matrix. And I can do that as long as I maintain my order. So here I have 1 over the determinant of A, my adjective matrix of A times A. This guy we know is the identity. So if this is the identity, then 1 over the determinant of A times the adjective matrix of A times A should get us back there, right? So because this is the identity, or that's our inverse, hopefully that makes sense. Now, if I want to figure out what the determinant of A is, You ready? You ready? If I multiply both sides by the determinant of A, and now it doesn't matter the order that I do these things in because determinant of A is a scalar, so it doesn't matter. But the determinant of A times the identity matrix is equal to the adjective matrix times A. So if I multiply my adjective matrix and my A, what's going to happen is I'm going to get an identity matrix that's close to an identity matrix. So what I'm going to get is that the determinant of A is going to show up in my diagonal, in my identity matrix, and all I need to know, I just pull that out and say, hey, look, there's my determinant. So we could have done that, right? If we had multiplied these two, in that example, turns out that the adjective times A is going to give us the matrix 14, 0, 0, 0, 14, 0, 0, 0, 14. So hey, look, here we go. There's our determinant. And you can try that out and verify it for yourself, but you know, have some fun with it. Could be exciting. I think that's all I have for Cramer's rule. That was a lot.